In this video, our focus is on distribution of molecular velocities. You would recall when we derived the kinetic gas equation, that's the pressure of an ideal gas, PV equal to 1/3 nmu squared, where u is the mean square velocity. It was assumed that the gas molecules in the given gas system, all of them move with the same speed, the same velocity in their given directions. Now, that is an assumption, because in real situation, the gas molecules, they do not move with the same velocity. And the reason for that is, like we know, during movement, these gas molecules, they collide with each other, and the collision process leads to transfer of momentum from one molecule toward another molecule. And of course, when momentum is being transferred, we expect differences in what? In velocity, because these gas molecules will either gain or lose kinetic energy. So the fact that collision leads to redistribution of speed. Are you following? It therefore means that in real situation, the velocities of these gas molecules when they are in motion and colliding are not actually the same as we assumed in deriving this formula. Please, it's very important for us to take note of this. That collision results to the redistribution of speed and what? Energy. Very important point for us to take note of. When gas molecules collide, speed is being redistributed, because I stated that due to transfer of momentum from one of the gas to another one, and that leads to redistribution of what? Energy as well, to gain or loss in kinetic energy. This led Maxwell and Boltzmann to use the theory of probability to establish the fact that the distribution of molecular velocities depend on temperature as well as the molecular weight of the gas. Once again, the redistribution of the molecular velocities of the gas molecules depends on what? The absolute temperature as well as the molecular weight of the gas molecule. The next video, we're going to look at the statement by Boltzmann and Maxwell, their probability distribution statement, and of course deduce the pre-exponential factor, also known as the frequency factor, as well as the partition function. Now, let us state Boltzmann's distribution law, right? It's a probability law, after which we are going to look at what the law is about mathematically. So, the law we have on the board here states that if the energy that is associated with a given state, a given level, a given condition is given as E, if that energy is given as what? E, then the frequency or the probability that that energy level will exist is given as the negative exponent of the energy of that particular state divided by the absolute temperature. Mathematically, that statement is given by what we have on the board here. This is the probability law, right? We have Ni is proportional to the negative exponent of the energy associated with that state, E subscript I. The I there represents the ith state. That's any particular energy level you're dealing with. The energy level 1, level 2, or what, alright? Divided by Kt. K here is Boltzmann's constant. T there is the absolute what? Temperature. Mathematically, we can remove this sign of proportionality and then introduce a constant. Here the constant is A, and we refer to that A as the pre-exponential factor. We can also call it the frequency factor. Take note of that, please. A is known as the pre-exponential factor or the frequency factor. EI already energy associated with a given state. T is absolute temperature of the state, which is also by implication the same as the absolute temperature of the gas molecule occupying that given state. K, of course, Boltzmann's constant, and then as I stated earlier, Ni here is the number of gas molecules occupying the ith state. Now that we've stated Boltzmann's distribution law, which simply tells us that if we say, okay, the energy of a given state should be E, then the probability that that state will exist, that condition will occur, is simply the negative index of that energy divided by what? The absolute temperature. In the next video, we're going to deduce certain things from this probability law. We're going to determine the fraction of molecules out of the total molecule of gases. Because of course, you know, we usually express the total number of molecules in the gas system as capital letter N. So out of that total number of molecules, what fraction can occupy a given state? If, for example, we have 20 molecules, and now we have energy level 1, level 2, level 3. How many fractions can be seen in level 1? How many fractions out of the 20 will be seen in level 2? How many of them will be seen in level 3 and in that order? Is that okay? So we're going to find out the value of that. We are also going to determine the partition function, also known as the sum over state. And then we shall find the value of the pre-exponential factor A. In this video, our aim is to determine the fraction of molecules occupying a given energy state following Boltzmann's probability distribution law. We are also going to establish a function known as the partition function, otherwise called the sum over states. Come with me, let's look at what we have on the board here, okay? If we assume that the total number of molecules of the gas in the gas system, alright, is given as capital letter N. And then let us now say we have different energy levels. Are you following? We have different what? Energy levels. So we have something like 1, 2, 3, 4. Let this be energy level ground state equal to 0. Then N1, N equal to 2, N equal to 3, and then in that order. Is that okay? Now you know that in the gas system, because of the redistribution of energy and molecular speed during collision, some of these gas molecules will possess more kinetic energy compared to others. And the more energy they have, then the possibility that they will occupy a higher energy level. Alright, now assuming that you actually have a total number of molecules, let's say N equal to 50. Out of these 50, some of these gas molecules will occupy this N1. Some will occupy N equal to 2, N equal to 3. You know, these are different energy levels. Are you following? Now, the number of molecules occupying each of these energy levels, this N equal to 0 is a ground state, alright? Energy level 1, 2, 3 above. We are using Ni to represent them, the number of gas molecules occupying a given state. So let's assume out of this 50, let's say that 5 is occupying N1, N equal to 1, and let us say that 20 is occupying N equal to 2, let us say that 15 is occupying N equal to 3, you know. So each of those number of molecules occupying each state, each energy level, we're going to use N subscript I for them. I there simply represents the ith state you are dealing with. So you can take I equal to 1 equal to 2, you know, just the energy level, the different number of states you have. Now, if we now say that we have such a number of molecules in energy level 1, energy level 2, energy level 3. If you add up each of these number of molecules in these different energy levels or energy states, if you add them up together, it will definitely give you what? 50, isn't it? Just think about a class where you have maybe 4 girls, 6 boys, and then if you want to get a total number of students in the class, you're going to add the six boys to what? 4 girls. Is that not so? You get 10. So the same thing, this 50, the gas molecules now have been distributed in different numbers, you know, to the different energy states. To get the total number of molecules, you need to add them together. Therefore, we have that total number of molecules can still be written as N1 plus N2 plus N3 plus continuously down to plus Ni. That is the number of gas molecules in any given state. And we can use the summation sign. That gives us this equation 2. Total number of molecules is simply equal to summation Ni, right? From Boltzmann's distribution law, we already established the value of Ni. Is that okay? That Ni is equal to the pre-exponential factor A multiplied by negative exponent of the energy of that given state divided by Boltzmann's constant times absolute temperature. Look at it. So if that is the case, you can actually substitute for Ni in this equation 2. Just pick this value, A exponential minus Ei over Kt. fix it up for Ni here, and then you get equation what? 3. This equation 3 gives us the total number of molecules in terms of the pre-exponential factor, the energy level of the energy value of that state, and the gas absolute temperature, as well as, of course, the constant, Boltzmann's constant. At this point, we now want to define the fraction of molecules occupying each of these states now. The fraction of molecule. When we're talking about fraction, you have numerator and denominator, is that not so? So to determine the fraction of molecule that can occupy any given state, all we need to do is to divide the number of molecules in a given state by the total number of molecules in the gas system. Go back again to our class example. You've got 6 boys, 4 girls. If you are asked what's the fraction of girls in the class, it's going to be 4 divided by the total 10. So we're going to apply same knowledge here. The fraction of molecules of the gas occupying a given energy level or state is given as this. Take note, Ni over what? N. And then we know the value of Ni, we know the value of N. So we can actually substitute them. Ni is given by this equation according to Boltzmann. And the total number of molecules N is given by this equation. So all we need to do is to substitute into Ni over N. You get this. Now look at this denominator. We do not sum constant when constant is multiplied by a given variable. You know that. For example, if you have 2x plus 2y plus 2z, to solve that you factorize the 2 out. You have 2 brackets x plus y plus z. So at this point we're going to factorize this a out. If you bring it out, it will cancel the numerator a. So the pre-exponential factors goes off. Are you following right? They go off, and then we'll be left with this equation. Look at that. The fraction of molecule occupying any given state will now be equal to negative exponent of the energy of that state divided by kT all over summation, addition of negative exponent of the energy level of any given, that is energy value of any given state divided by Boltzmann's constant times absolute temperature. Equation 4 defines or gives us the value of the fraction of molecules occupying any energy level or energy state in a given gas system. The denominator, look at it. The denominator, which is summation exponential minus energy of any given state divided by Boltzmann's constant times absolute temperature, is what we call the partition function, also known as the sum over states. Please take note of that. In the next video, we're going to look at the value of the pre-exponential factor A. Now that we've established the fraction of molecules, occupying any given energy state, and we have also determined the partition function, that is the sum over states. We now want to deduce the pre-exponential factor value, that is the frequency factor value, right? Now to do this, we are going to consider the probability that some fraction of gas molecules moving in, say, x direction. We'll start our analysis with x direction. Whatever we get, we can now convert to other directions, y and z. So we're going to consider the probability that this fraction of gas molecules moving in x direction, their velocity value is between ux and ux plus dux. What's the meaning or implication of these two velocities here? When the gases start moving, they move with a certain velocity, let's say the initial velocity. Then after collision, it's possible that their velocities will increase, leading to an increase in kinetic energy as they move. So considering that their final velocity after collision is ux plus dux, that is to say, an increment dux, an increment in the value of the original what, or the initial velocity. So we want to consider the probability that these gas molecules, this fraction, as they move in x direction, their velocities will be between these two velocities, this initial and this final. Is that okay? So we're going to now apply the definition, the probability definition for the fraction of molecules moving in that x direction. The equation is going to be given by equation 1 here. Nx over n, that is fraction of molecules of the gas moving in x direction, being equal to, we are picking just the numerator of that probability of obtaining fraction of molecules moving in a given direction or seen in a particular energy level. We are picking just the numerator. We will drop the denominator because we know that that denominator, which is the partition function, is common to all the states. So let's keep it aside and focus on the numerator. So with this term, the numerator term, we are going to integrate it with respect to what? X. We're going to integrate with respect to x to help us get that velocity we are talking about. The probability of the velocity between these two velocities. And then that being the case, on integrating this term from negative infinity to positive infinity, taking our energy to be kinetic energy, of course this gas is in motion, so it's kinetic energy, which is 1/2 mux squared. Take note, I'm defining this with respect to x-axis now. So we're going to get this and then do the integration with respect to velocity in that x-axis. Now this integral, look at this integral term, is equal to root pi over a. Where root pi over a, this a is some constant there, is that okay? So if this integral is equal to root pi over a, multiplying it by this pre-exponential factor, which of course is a constant, so it has to come from this integral sign here. It has to come out, you know. We don't integrate constant per se. And so if you multiply this value, root pi over small letter a, by this pre-exponential factor, it will converge to 1. The value will converge to 1. So this whole term is equal to 1. This a here has a value which is equal to m divided by 2kt all raised to the power 1/2. Take note that these values we obtain for this integration is based on kinetic consideration, alright? They are based on kinetic consideration. These are values that you're going to get by integrating this. Does that make sense? Alright, now moving on, we are going to have the value of this pre-exponential factor to be equal to m over 2 pi kt in bracket raised to the power 1/2. How true is that? If we know that this small letter a, this constant, is equal to this value, solving this part of the equation, that is pre-exponential factor times square root of pi divided by a, equal to 1, then this a, which has this value, will multiply this one, so that a root pi will now be equal to this value of a. Making this pre-exponential factor subject of the formula, you would get the value to be m all over 2 pi kt all raised to the power what? 1/2. And this is the value of the pre-exponential factor. Please memorize that equation 2 star. 2 star star. Very, very important. Memorize it, okay? You need to know the value of that pre-exponential factor a. Now, this small letter m here in the numerator is simply mass of one molecule of the gas. So what if now you're dealing with the total molecule, the total mass of the gas, where we use molecular weights, capital letter M. In that case, all you need to do, the denominator, the Boltzmann's constant will be replaced with the universal gas constant R. Is that okay? In the next video, we are now going to apply this knowledge. Being that we've obtained the value of this pre-exponential factor, we are going to substitute it here now to get the probability that some fraction of gas molecules moving in x direction will have velocity value between ux and ux plus dux. After which we'll also see that of their movement, you know, in y direction, and that in what? Z direction would get their probabilities.